Hello, everybody. We are here with our new EDS talk, EDS distinguished lecture talk from our channel. We are from the IEEE Solid States EDS joint chapter, and we're here with Professor Gilson Wirth, that we are honored to have him here to present the talk Charge Trapping in Semiconductor Devices from Device Level Modeling to Circuit Analysis. Professor Gilson Wirth received the bachelor and master degree from Federal University of Rio Grande do Sul in 1990 and 1994, respectively. In 1999, he received the doctoral engineer degree in electrical engineering from the University of Dortmund, Germany. He's currently a full professor in the electrical engineering department at University Federal do Rio Grande do Sul since 1927. From July 22 to December 26, 26, he was professor and head of the computer engineering department at Universidade Estadual do Rio Grande do Sul, Wirth. His current research work focuses on modeling and analytical simulation of charge trapping in the context of bias temperature instability, low frequency noise, and hot carrier degradation. He has also worked on ionizing radiation effects on semiconductor devices. He focuses on collaborative work with academia and industry. He has established successful collaboration work with companies and research groups in Europe, North and South America, and Asia. He is currently a distinguished lecturer of the IEEE Electron Device Society. He also was a distinguished lecturer from the IEEE Circuits and Systems Society from 2010 to 2011. It's here really a pleasure to have him here, and thanks for coming. Welcome to our presentation.
Thank you, Sandro. Thank you very much for the nice introduction. Thank you for being the chair of our chapter and making this work on behalf of all of us. I would like to thank Sandro and the other chapter officers and all that are part of the South Brazil Solid State Circuits and Electron Device joint chapter. It's really an honor and a pleasure to deliver this lecture. And for those who are not yet members of the IEEE Electron Devices Society or Solid State Circuit Society, I strongly recommend joining. I'm sure you are going to like it. Let me just put the pointer here, pointer options, yes. And so please visit the Electron Devices Society webpage. There you can get much more information about the Electron Devices Society, its activities, and how to join. Well, we are going to talk about charge trapping. Charge trapping is related to defects between the semiconductor and the dielectric, the oxide interface, and the defects maybe itself. Well, as you know, the field effect transistor was proposed about a century ago. And yes, charge trapping is nothing new. Charge trapping has been there since the proposal of the field effect transistor. And at that time, it was a major issue hindering the fabrication of a working field effect transistor. It took a long time, about 40 years, until field effect transistor could be realized. Because you need a very good quality of the dielectric and of the semiconductor itself. So silicon dioxide was really a very good advance that did enable the semiconductor industry for decades. And at the beginning, we had the planar device, and we have evolved over the FinFET and now nanosheet devices But you also have the same idea. A field effect transistor where you have a semiconductor, you have a dielectric, and you have defects in that. So even today, charge trapping is a major reliability issue and is expected to stay a issue for probably a long time yet. And as we will discuss in scaling, the impact of a single charge trap increases. So it's actually becoming a, let's say so, a larger problem. And it's also relevant in other devices, not only in silicon and silicon devices, but also in gallium nitride, for instance, based devices where you also have charge trapping, of course, and memory stores like sometimes called resistive switching devices. So it's not only related to silicon, but and the silicon field effect transistor, but to other materials as well. Well, and first we will talk about the basic ideas of charge trapping in time and frequency domain. So, what are the key parameters for modeling? And as we will see, charge trapping is relevant also for bias temperature instability, also known as age. 1 over F noise or RTN. It also plays a role in hot carrier degradation, since you know hot carrier degradation is also related to the creation or occupation of defects in the oxide, so also charges that are going to be present in the interface or in the dielectric. So charge trapping is something that has many faces, let's say so. And today we will focus a lot on circuit analysis, circuit simulation. And I chose the case to the ring oscillator because I think the ring oscillator gives you the idea of how charge trapping impacts circuits in general. Because you know, ring oscillator could be seen as a digital circuit because you have an inverter there, but also gives you a basic idea of how charge trapping would appear in the frequency domain. So the idea is going from frequency domain to time domain and see the relation. And at the end, I will present some conclusions. And also, if you talk about the time window, because you know, if you look at charge traps, we're always are going to ask, okay, how many charge trappings are that impact my circuit? And the answer would be, well, that depends on the time window, on the maybe could say the frequency bandwidth that is related to the time window. We are going to discuss that in detail. Well, and then first you have the 1 over F noise. Here the red circles represent the charge carriers. Let's think about the electrons, represent the electrons. And here you have time, and here you have current. On an ideal device without any noise, if you have a constant bias, constant drain bias, constant gate bias, you would expect the current to stay constant over time, not vary over time. But of course, you have noise there. In here, we are talking of charge trapping. So if a defect, that is this gray circuit here, captures an electron, then you have one less electron in the channel, and also this charge is going to be a source of scattering that's going to affect the mobility. So I have a reduction in number of electrons and have a reduction in mobility, and then the current that flows from source to drain is going to be smaller. So if a charge trap is occupied, a capture event, you have a smaller current. If you get the charge emitted back to the channel, again, you have more carriers in the channel, larger number of carriers, and you don't have the source of scattering. And then you have a higher current. So this continuous capture and emission is going to generate a fluctuation, a variance in the current. You could see this as a current varying over time, or also as a threshold voltage jitter in the sense that the threshold voltage itself fluctuates, or current itself fluctuates. Well, this is the case for a single charge carrier, for a single trap. You have many traps, you have the cumulative effect, the cumulative contribution of many defects. So basically, we could see that you have a threshold voltage fluctuation over time that depends of the state of all of the observable traps in a given instant of time. This is the case of random telegraph noise. As we will be seen, we are going to see in frequency domain, it can be seen as 1 over f noise. But we also may have another kind of defects. Actually, forget it's not another kind. It's have a defect that has a different behavior regarding capture and emission. That here you have a defect that keeps capturing and emitting, but you have a defect for which the capture time is much shorter than emission time, so that by far the capture event is much more likely than emission event, so that once the defect captures an electron, it does not give it back to the channel because the emission time is quite long. Then you will see that you get a capture event, and then you have the next defect that also captures an electron. So you have successive capture events, and you don't see emission events. So what you see is the current degrading over time. So the current decreasing over time. So this may be seen as aging, also known, in this case, bias temperature instability. So you may have the relation of the capture and emission event are similar or equally likely, then you will have RTN, random telegraph noise. But if by far the capture event is the most likely, you are going to see capture events and no emissions, then you have BTI or aging. Well, so it's basically what we do. We do the modeling from device level, that means transistor level, and then go to the circuit level. As I said, our case study will be inverter and then ring oscillators. And we'll also talk about phase-locked loops, PLLs, based on ring oscillators. Then you need to know what are your random variables. Since it's going to be a statistical model, well, what are your random variables? First is the time constants. The time constant, the emission and capture time constant, which we assume that they're uniformly distributed in a log scale. Another option would be assume it to be distributed according to a log normal. For the modeling framework itself, we could choose any one of them. The modeling framework does not change, but of course, for doing the simulation or for doing the circuit analysis and show some results, then you have to choose one, and we choose the uniformly distributed in a log scale. And also the number of traps are a random variable that we assume is Poisson distributed. And the amplitude of the fluctuation induced by a single trap is also a random variable, which in both cases, when simulation, we assume that it's exponentially distributed. But as said, for the model in general, you do not need to do these assumptions for the model itself. Of course, for you getting some results, then you need to make it, the assumptions. Well, so the key parameters are the current fluctuation induced by a trap or the threshold voltage fluctuation induced by a trap. That are related. You can translate using the transconductance from one to the other. And also the number of traps. And the number of active traps depends on the time window or the system by bandwidth, as we are going to discuss. So actually, the more basic parameter will be the trap density per unit area and frequency window or time window. And important, both parameters are the same in time and frequency domain. And of course, both parameters are the same. The assumptions are the same for bias temperature instability and random telegraph noise. Unifies bias temperature instability, random telegraph noise, and low frequency noise. Well, here is the relation between time and frequency domain considering a single trap. If you look at a single trap, you will see that you have random capture times and random emission times, and you have the amplitude fluctuation. If you look here, you have the current over time. If you translate this to frequency domain, you will have, for each single trap, you will have a Lorentzian, which is one of these red lines here. You have a plateau, and then it goes with 1 over f squared. So it goes down with 1 over f squared. And the corner frequency is related to the capture and emission times. The faster the trap captures and emits, the higher the corner frequency is going to be. Since each trap has a different corner, since each trap has a different capture and emission time, so has a different characteristic time constant, each trap has a different corner frequency. And if you add the contribution of many traps, you may see the blue line, the blue line, that is the 1 over F noise. So the 1 over F noise comes from the contribution of many traps. And some, if you have see some examples short, sometimes for small area devices, you do not see for a small area device the 1 over F noise. And then some people say, hey, we have Lorentzian noise for the 1 over F instead of 1 over F noise for a small area device. Of course, but if you make the summation, if you make the average of many single small area devices, you usually see 1 over F noise. So the average expected value, even for a small area device, if you average over many devices, is still 1 over F, even for small area devices. Oops. Let me go to the next slide here. Yes. So this is an example where here you have, for instance, the blue line, the green line, and the yellow. You have different evolutions over time. And you can relate each one of them. Here are many measurement devices. Here in frequency domain, here is the related time domain behavior. So each one is going to have a different corner frequency, a different amplitude. But what is interesting here, you can relate the power spectrum of the 1 over F noise. If you integrate it over time, you can relate it to the variance of the drain current or the threshold voltage, remembering that you can relate the fluctuations in drain current to fluctuations in threshold voltage. So what's the basic idea here? You have a relation. We are going to see that what's important when you are looking at the behavior at the circuit level, you need to ask, okay, I have a transistor, for instance, and it has a drive current, a drain current. And what is the variance of the drain current over time? How does the drain current fluctuate over time? And a good measure for that is the variance of the drain current evaluated over time. Well, it is related to the power spectrum in frequency domain. So in time domain, we evaluate the variance of the drain current or the variance of the threshold voltage. And in frequency domain, we evaluate the power spectral density, and they are related, as we are going to see. Okay, next slide. Well, and as I commented, it's important to look at the area scaling. Let's look here at two examples here. One is the following. Let's look at the 100 nanometer device. Well, if you look at the number of expected carriers in the channel, I mean the number of the expected number of electrons that inversion layer, you will see that you have about 1,000 electrons making up the inversion layer, so the conductive channel. If you go to a much smaller device, like a 16 nanometer one, you have only dozens of electrons. So, well, you may expect that the impact of one electron, if you have only a few dozens, is much larger than when you have thousands of electrons. That's what happens. So the impact in drain current percentually or in threshold voltage increases as the area goes down, and the number of traps is expected to be proportional to the area. So with downscaling, the number of traps actually decreases, and the number of traps per device decreases. So the number of traps per device decreases while the impact increases. This is going to lead to a larger noise, a larger variance of drain current, and it's also going to lead to a larger device-to-device variation. When we talk about device-to-device variation, let's see the next slide. So here is the example for two devices of the same size. And here I would like to start introducing the concept of inter-device variance and inter-device variance. What do I mean with inter-device variance here? Well, here you could have the threshold voltage or the drain current over time. So you see that the threshold current or the drain, the threshold voltage or the drain current, they change over time. So in a single device, the parameter, the current or the threshold voltage fluctuates over time. So it's not always the same. So we have an inter-device fluctuation. Depending on the instant of time where you look at your device, it may be carrying a given current. At another instant, you look again, the current has changed. So this is an inter-device variance. So one of the questions is to expect what is this expected in in the other means, what is the mean value of the variance of drain current over time for a given size of device for a given device. This is the inter-device, expected value of the variance inside a single device over time. But if you look at different device of same size, so the designer did design the device with exactly the same size, exactly the same bias point. So they should, in terms of electrical behavior, they should match, but they are not going to match. You may have a variance in the sense that one device has a different number of taps with different amplitude. For instance, here I have one device, same size, the device A, that has a few taps with large amplitude. Here I have device B that has only one tap with small amplitude. So I also have inter-device variance. And interesting to note, even if the device would have same amplitude of traps, would be same number of traps with same amplitude, you still would have this time-dependent mismatch. So this causes a time-dependent mismatch in the sense that it's a mismatch that changes over time, that depends on the state of the traps over time. So this is the concept of, let's say, time-dependent mismatch. I hope it becomes a little bit more clear in the next slides. Well, I will go very, very quickly because, I mean, the idea is not to go that much about the mathematical details of the modeling. It's much more go to get insight on circuit behavior regarding jitter and time-dependent skew. We'll talk quickly about that. And then, but well, to arrive to that, we have to, of course, do the modeling. So for random telegraph noise and 1/f noise and BTI also, the model parameters are the same, are basically the number of traps, the amplitude contribution of the traps, number of traps and amplitude contribution of the traps. And of course, it's going to be the summation of the different traps found in the device, either evaluated in time domain, where you follow the state of the trap, so the switching of the trap, switching between occupied and empty and so on, and in frequency domain, the summation of the different Lorentzians. And you can extract, that's I think is very important, you can extract the parameters, which are the same, either in frequency domain or in time domain. So once you did the characterization in frequency domain, you can make the simulation in time domain and vice versa. And if you, and you can extract all the parameters. You can do the parameter extraction based on the modeling itself. Okay, you have here, yes, here. And from the modeling, it comes that the average noise of the average 1/f noise increases as air is scaling down. But even worse, much worse, I would say, is that the variance from device to device increases much faster. While the 1/f noise increases with 1/area, the variance between devices increases with 1 of the area on the third power. And of course, the same is valid for time domain, since the models are, let's say, so the same. The sense that are the framework the same, they are physically the same. And you can see this here. Here you have a not so small device with a channel width of 300 nanometers and channel length of 300 nanometers, 40 channel length, 40 nanometers, and a much larger device. What you see here, you see that the y-axis are on the same scale, same for the x-axis. So you can clearly see that here you have an increase in the average value. Here you have an average value about this. Here you have a much larger average value. So as the area decreases, average value increases. But you can see that the spread, the variance increases much faster. So, well, let's say that's for the design may be a problem. So have a large variance among devices that by design should be the same. Well, and as I have been talking, you can extract the parameters, the parameters that are the amplitude of a trap and trap trap density from the model itself. So if you make the measurement either in frequency domain or in time domain, you can do the parameter extraction in frequency or time domain. Well, let's go now to circuit analysis. This is where I would like to focus a little bit more. Okay, so basically, and this is of a inverter, but it could be also a proxy for an analog circuit, let's say an oscillator or something like that. Because usually what you have a current source driving a load. So this is many times happens also in other kind of devices like LC tank oscillators and so on, where you have a transistor, a drive current driving a load. In this case, we have the PMOS driving the load, charging the capacitor, or the NMOS discharging the capacitor. So basically, you have the delay of the inverter is related to how fast you can charge or discharge your node capacitance. And of course, if you have always the same current, so I have absolutely no noise, the time to charge or discharge is always going to be the same. So if the current is deterministic, in the sense it's always the same current, the time to charge and discharge are going to be the same. We are assuming here that is the time to charge or discharge the capacitor of VDD, the half value of VDD. But as we know, we have noise. So we have not a constant drain current. Here is time, and the capacitor voltage over time. Here you have the different possible, let's say, so drain currents. And you have the noise on top of it. So if most of the time the trap is empty, so that most of the time they have the higher current, it will take shorter to charge the capacitor. On the other hand, if most of the time the trap is occupied, is in the low current state, it will take longer. So the actual time to charge or discharge the capacitor depends on the drain current, and the drain current depends on the state of the traps. So it becomes a random variable. So sometimes you will have a shorter delay, and sometimes you have a longer delay. So traps occupied, longer delay, traps empty, shorter delay. Larger current, shorter current, depending on of the trap. If you have an oscillator, in the case of a ring oscillator, sometimes you may have a longer oscillation period. Let's take, for instance, just as imagine that you have traps in each of the inverters, and let's say so at some instant of time, all traps are occupied, you will have a longer oscillation period. If all are empty, you have a shorter oscillation period, and you may have any combination of that. You may have then different delays in between. And this is related to phase noise, because ideally you will have a very definite oscillation period. In the sense, always you would have the same oscillation period. In the case of a square wave, you would have a discrete spectrum with the fundamental and the harmonics. In the case of a square wave that we would like to produce, for instance, with a ring oscillator. But you will not have this. You will have sometimes a longer oscillation period, sometimes a shorter oscillation period. Same may happen with other kinds of oscillations. And then you will not have a very definite oscillation period, but it may have shorter or higher or lower frequency. And this is related to phase noise. And you cannot have interference between neighboring channels if you assume that each each channel is defined by a carrier frequency, and if they overlap due to noise, phase noise in this case, or could be RTN if you are regenerated from a VCO-based PLL, then you will have phase noise, and this will limit the capacity of the communication channel. So we are starting to look at the circuit behavior. But before we look at the circuit behavior, I would say that it's important to look at the time window. What is a time window? Oh, sorry, should click here. Why is not changing? Oh, it changed too fast. Sorry, I got a small problem with the change of the slides here. Yeah, now let's press once and wait a second. When it freeze. Okay. Okay. I think this is the next slide. Yeah, it could be this one. What's the time window? The time window, okay. If you look, here is the current or the drain current over time. If you look it in a linear scale, you may think that the variance of drain current or the variance of drain voltage does not depend on the time window. But if you look, if you put the time in the log scale, yes, you are going to see that as time evolves, the variance or the envelope increases over time. And this is related to charge trapping. We can understand this looking at, this is a measurement of a single trap. Here is the time, and here is the current fluctuation. If I look at a very small time window, what means a very small time window? A very small time window is the time window that is so small that is smaller than the average capture or emission time constant of the trap. So if the time window is small, I hardly going to see the trap to change state. So if I have a small time window, the trap is not going to change state. But if I evaluate the variance, for instance, of drain current over this time window here, the variance will be quite small. If I evaluate the power spectral density of this time series here, it's going to be small also. But if I increase the time window, this red window here, I will see that the trap switches many, many times in the time window that I'm observing now. So if the trap changes state many, many times over this time window, yes, it is going to contribute to a variance, to a variability of the drain current. And of course, if I make the Fourier transform, if I look this in frequency domain, I will see a high power spectral density. So the variance, we are looking more at the time domain now. The variance of the drain current that I'm going to see depends on the number of traps that are active on the time window of interest. And the longer the time windows, as the time window increases, these lower traps start to become visible, start to contribute to the variance of drain current over time. This could be seen here if I look at the variance of the drain current over time in shorter time windows, in time windows where the observation time is much shorter of the characteristic time constant of the trap, it does not switch state. So I see no variance of drain current. As the time windows increases, I start seeing many capture and emission time events until it saturates. After you see a dozen, let's say so, of capture and emission time, capture and emission events, it saturates. So each trap is going to saturate at a given value. And if you have many, many traps, you get the summation of it. So I could put here the time window in frequency, the time window in log scale, the time window in log scale, and the variance of drain current. So as time goes by, more and more traps become visible, become active in the observation time. And so the observed variance of drain current increases over time. The observed variance of IC on drain current increases over time. So basically what I have, the observed variance of drain current or the observed variance of the threshold voltage increases over time and depends on the expected number of traps that I see in the time window of interest. And the expected number of traps depends on the time window where I have a maximum time, where the maximum observation time, but I also have a minimum time. What's the lowest limit of the time window? For our case study of interest, the minimum time, so what I call there the mean the lower limit of the time is going to be the propagation delay. I hope it becomes a little bit easy to understand here. Let's think about a trap that switches state about 100 of time in the propagation delay. So in the time where I go from 0 volts to VDD over 2. So here is, I'm charging the capacitor to half of VDD. If it switches about 100 of times, so in each time I observe a propagation delay, it's gonna switch about 100 of times. So basically, the lower limit is the propagation delay itself. The lower limit is propagation delay itself. So the inverter acts as a filter. A signal that is in the input, let's say, so is acting this inside the traps are acting inside the inverter, but you could think in this way. If I have a signal in the input that is much, much faster of the propagation delay, the output is not going to change, it's not going to affect the output. So the inverter could be seen as a low-pass filter with with the corner frequency related to the propagation delay itself. So, but now if a trap is switching, let's say, so it stays at one time, it's always occupied. I get a lower charging, a lower current, so a longer charging time. If in the next observation the trap stays all the time empty, I will have a higher current. So if between propagation delays the trap changes states, remains in the same state during, let's say, the first charging, trap empty, the second charging, trap occupied, is gonna contribute. It's gonna contribute a lot to the variance in propagation delay. I hope it becomes more or less clear. But so the lower limit is the propagation delay of the gate. In this case, the lower limit, a good measure for the lower limit is the propagation delay, in this case of the inverter, and the higher limit is the observation time. The longer I observe, the larger the chance I will observe more traps. So we can then talk about time window. So usually you have, what is a time window? You have a measurement of the transistor itself, of your circuit. You are observing the oscillation of your ring oscillator, the oscillation of your phase locked loop, of your PLL, any circuit. So you make a measurement over time. And this original time series may be split into smaller segments of same size. For instance, into half, and then 4 quarters, and so on. And you can evaluate the parameter interest over each one of the time windows. So first, I may evaluate it for a longer time window, a smaller time window, even smaller time window, and so on. So I can have many time windows of many different size, splitting my original time series in smaller segments of same size in our case. And well, so the time window, as I comment, is related then to the observation time. Let's look much more at the time domain. So the minimum time, that in our case could be the delay of the inverter, and the maximum time, that would be the observation time itself. And of course, you can relate this to frequency domain. We'll go back to this quite soon in the example of circuits. So in circuits, what we have now, we'll show you a few results of circuit simulation, and it's important to know how the simulations are performed. This is what we do. We have a ngSpice code that's is open source, written in C. where in this C language, in this, we include the trap activity. So each transistor is going to have traps, and traps have a given time constant, characteristic time constant, and a characteristic amplitude contribution. So actually, in the simulation itself, the threshold voltages changes over time. And of course, also, then the drain current changes over time. So if you run a usual SPICE simulation with constant bias and no noise, if you look at time and the current over time, you'll see a constant current. Now the current is not going to be constant over time. The current is going to change according to trap activity. And some results and jitter in ring oscillators. But well, and now since it's to understand how it relates to the time window, it's important to clearly define the different jitter metrics. So we have the cycle-to-cycle jitter. What's the cycle-to-cycle jitter? It's basically the variance that we the expected variance that we observe, the expected difference that we see, the variance of the difference between two consecutive oscillation periods. You just look at two oscillation periods, one and the next one. And period jitter is something different. Period jitter looks at the variance of the period over a given number of oscillation periods. So cycle-to-cycle jitter is the same, I could say so, in our case, as period jitter if you look only two oscillation periods. But sometimes you are interested in a larger number of oscillation periods. The next slide, I hope you have to put this concept a little bit more clearly, I hope so. And then also have absolute jitter. But absolute jitter is the variance of the summation of any periods. So you have a given time window, you look at how the summation varies over time. So it's much more related of the accumulation of delay variance over time. I hope. Here is then we evaluate it. So this is the definition. Here is how is expected that the jitter evolves over time. But here time actually is the number of oscillation periods. So the proxy for time is n, the number of oscillation periods. So the time window itself goes with n, because usually people report jitter as a function in terms of the number of observed oscillation periods. Okay, and you will see that cycle-to-cycle jitter is not expected to depend on the time window. So let's look at the jitter evaluation. And important to say, almost forgot to say, please see here, there is no relation to an ideal clock. There is no the concept of an ideal clock. All what we look at how the oscillation period vary over time without the relation to an ideal clock. For instance, if you have a oscillator that have always the same period, you have, of course, no cycle-to-cycle jitter, you have no period jitter, and no absolute jitter. But now let's see how a trap can change this. Let's look here. Here you have, in this example, that a trap remains occupied. And here that the trap becomes empty. And I would like to call attention for the difference between absolute jitter and cycle-to-cycle jitter. If you look at cycle-to-cycle jitter, here you have just one trap. In the general case, they have many traps, with different amplitude contribution. Here you have only one trap. If I look here, if you have the trap occupied, the oscillation takes longer, so the period is longer. If the trap is empty, the oscillation gets faster, shorter period. Well, what we could say, here you have this trap that's a slow trap. If you had a fast trap that switches status between each state, you still would have then a longer period and a shorter period. And actually, if evaluated over these 6 oscillations, the period jitter would be the same, because it would make the variance of between 6 values, which of them the 3 last ones are equal and the 3 last ones are equal. So you mix them. If the happens a fast and short, a fast and short, a fast and short, the variance of these 6 numbers is the same. It does not depend on the sequence. So this is period jitter. But just look at the variance of the oscillation period over a given time window. But now, look at the summation, what happens? Here, I have a given summation, here a longer summation and longer summation. So this is like a correlated, where you have a correlated effect that the trap remains empty, creating a correlation between successive periods. And here it remains, here it was occupied, here it remained empty, also creating a kind of a correlation. So what you see in relation, where here you have, this is not the ideal clock, this is just the average, the mean value of the period over these 6 periods. So if I look here, I compare the summation according to what was expected compared to the average value. So now, here I have a dislocation regarding the expected point, the expected transition. Since this one is also going to be longer, the dislocation, the difference increases. Here it increases further. So if the trap is low and remains occupied, it contributes more to the absolute jitter. So the absolute jitter is going to increase. And that's why the absolute jitter increases over the time window. So a slow trap creates a kind of coloration, shifting the expected value of the transition in relation to the one that would expected, considering the average value of the clock. So this is the definition. So it's the variance of the summation of the clock period over any periods. The variance of the summation over any periods. While the period is the variance of such. For absolute jitter, the variance of the summation. For period, just the variance, not considering any kind of accumulation. And here are the results. First, cycle-to-cycle jitter. As expected, the number, as the time windows increase, as I go observing more and more oscillation, a larger and larger number of oscillation, the cycle-to-cycle jitter does not increase with time window. Why? Because regardless of the size of the time window that I'm observing, the time window for noise, the time window for induced noise is just only the time window between 2 oscillating periods. So if I observe 100, I always looking at the difference between 2 successive ones. So actually, the time window in this case is 2 times the oscillation period. So the traps that change state between one oscillation period and the next one. So the observation time, I mean, the time that the traps have to switch is just 2 oscillation periods. A slow traps that takes long to switch is not going to switch between 2 oscillation periods. So it does not contribute to noise. And this does not change in regard to the number of oscillations observed, since I'm looking only to the difference between 2 oscillation periods. And unfortunately, I don't have time to talk about that, but the cycle-to-cycle jitter increases as we decrease VDD, as we decrease the voltage, the voltage which the oscillator is operated. That can be seen. I think this I can talk very quickly because it's related to the number fluctuation. Of course, you have not only the number fluctuation, you have also the related mobility. But imagine you have a given drain current, what a large VDD, a large operation voltage. The channel is formed by a lot of charge carriers. So if I, let's say, 100 charge carriers in the channel and one gets trapped, you have a change, a percentage change of only 1%. Now you go a very low VDD. Let's say you have only 10 charge carriers performing the inversion layer. If one gets captured, well, the the relative change in current is going to be about 10%. And then this leads to that you have a larger cycle-to-cycle jitter, a larger jitter if you go to lower VDG, to lower bias. Well, this is also valid for the other types of jitter, cycle, period jitter, and absolute jitter. I'm running out of time. And then now you can see, as we expect, if you look at period jitter, the jitter, yes, it increased with number of oscillation cycles. See, here I have number of oscillation cycles, that's the time window increasing, and here the period jitter. So if I go increasing the time window, the jitter increases. But if I look at the absolute jitter, it increases much, much, much faster. This is due to cumulative behavior, you know, because I have a very slow trap, let's say that for 100 cycles, observed cycles remains occupied, it is going to make that during these 100 cycles, the successive 100 cycles are going to be much slower. So if I compare it to the expected value, the 100th cycle is going to happen at a time that it's much, much longer than expected. Now, if I look at one time in cycle, the dislocation, the difference is going to even larger. So there is this kind of correlation that makes that it basically increase with basically the number of cycles on the square. Now I can go back again here, and you see that for period you just have the log of time, the log of the number of oscillation time, the log of the number of oscillation cycles. Here you have it proportional to n on a power, where for the case of RTN, for the case of low frequency noise, because of this kind of correlation due to slow traps, is going to be this power alpha here is going to be very close to 2. For white noise, for thermal noise, it would be expected to be closer to 1, while for jitter induced by trapping is going to be expected to be close to 2. You have this cumulative behavior. Okay, and by now, these values here, they are the expected value of the jitter. So, and also here, this is the expected value of the jitter, based on the expected value, the average value of the number of traps, the average amplitude, and so on. But as we know, each device is going to be different number of traps with different amplitude. So the same spread that you see in 1/f noise, people use it to see this spread in 1/f noise, the same spread they're going to see in jitter. So you have not, each device is different from the other. So also in jitter, if you look here, let's in a small device, you have a given jitter. So this would be the average value. By now we have been talking about the average value. But of course, you have, let's say, 100 ring oscillators with all transistors of same size. So each one is going to be different jitter. And as you go to smaller size, the value of the jitter increases, but not only the expected value of the jitter increases, also the spread. So you have larger jitter, but some devices that have a really much, much larger jitter. So you have also this variance of jitter among oscillators. So the inter-device variance grows faster than inter-device variance. What is the inter-device variance? The inter-device variance is the expected variance of drain current in a single device. Okay, this is the inter-device. The inter-device, yes, the inter-device. But you have different transistors, they will behave differently. So if you have this, here you look at the average jitter, let's say a ring oscillator made in the larger area, and you go to smaller area. The average value of the jitter increase, but the spread, so the devices are going to be quite different from each other. So, and this is predicted by the model. As we saw, the average value of the jitter increases with 1/area, but the spread between devices increases much faster. And regarding the time window, if you have, for instance, the PLL, here we have the jitter accumulation of 500 PLL as a function of time. And for lower accumulation times, you see the jitter increasing. But, you know, the phase locked loop, it can correct the variation, can correct the jitter. So if the accumulation time comes long, then the setting time of the PLL, the jitter stops to increase. So you should only see the increase of jitter for shorter than the PLL settling time. So it depends on the bandwidth, and you can relate it to the 1/2 noise since you have a bandwidth. Here we have the transfer function of your PLL. H is the transfer function. In this case of your PLL, that for longer times or lower frequencies corrects it. So as I said, you need to look at the time window. So in this case, the time window would be limited. The higher limit of the time window would not be, in the case of PLL, would not be the observation time, but would be the settling time of the PLL or the bandwidth. And just to close here, I'm almost on time. It can be even also a problem, for instance, for clock distribution networks. If you have a clock source and the clock propagates, the clock comes from here. Let's look at this path here. It goes over this one, and then let's say it's over this one. But see, here, ideally, this inverter and let's say this inverter, they should have the same delay. And this inverter should also have the same delay. So that the clock edge propagates and has the same delay from here to here, and the same delay from here to here. Regardless of the delay, if it's long or if it's short, if it's deterministic, it is always the same. It will arrive at the same time at here and here. But now we know that we have different traps here and different traps here. So sometimes this, if here the traps are empty, maybe short the propagation delay. So the clock edge arrives faster here and slower here, so I have a skew. And other times it could be opposite. It propagates faster here and slower here. So you have a skew that changes over time. So skew is not the same in all time, in all observation. So it could be seen as a time-dependent mismatch. So where you have a mismatch between the delay of the gates, and this mismatch changes over time. So it could be seen then as a time-dependent mismatch, causing a time-varying skew. So a time-varying mismatch causes a time-varying skew. Because, you know, if the mismatch is always the same skew, but if the mismatch changes over time, varying skew over time. This could be a problem for synchronous circuits. Well, and also in this case, also BTI, because we have aging here, and aging, you know, is also not deterministic. One path may age faster than the other, because also aging over time, let's look at here, is also stochastic, because some devices may have a few traps with a small amplitude and others many traps with large amplitudes. Also, aging may be seen as a time-varying mismatch, so as a mismatch that varies over time. And also hot carrier degradation, about to mention, also charge trapping effect. Hot carrier degradation may also induce a mismatch that changes over time. So random telegraph noise, bias temperature instability, hot carrier injection may cause mismatch that varies over time. And okay, this is a conclusion that we presented a statistical model that goes from device level to circuit level. And I think it's very important, this statistical model, because if it was not stochastic, we would not have, for instance, this time-dependent mismatch. If it were not stochastic, no jitter, no time-dependent mismatch, no time-dependent skew. And I would like to thank the many people that involved in this work. I mean, I really like working with charge trapping, something that for me is fun. I mean, I like it really, and I have the very happy to meet another people that also like this topic, and my students, I have learned so much from my students. I would like to thank them so much for the time, to the discussions, and of course also the colleagues here at our university, or the other university in Brazil, the people at Arizona State, Drag Savasileska, Kevin Cow, at TI, formerly Ralph was at Infineon, and SP, people, IMEC Ben Caxer, Felipe Rossell, Franco Jacopo, Maria Toledano Luke, people at NXP like Andre Scholten, sorry, Andres, if I do not spell your name correctly, and people in China. We had also the opportunity to Kaishen, and it's very nice to have the opportunity to learn so much from you, and was a fun time discussing these topics for you. Okay, here I finish my presentation. Thank you so much, and sorry for taking a little bit longer than I was expected. I expect to take about 45 minutes. It took longer. Sorry for that.
It was fine. It was fine. Don't worry about that. It was a great talk. Great talk indeed. We have several comments, a lot of engagement here, and we have some questions from the audience. I will take them in the order, right? So the first one is from Mr. Shiva from India, and he's asking about which MOS device would better be used while designing low noise circuits, and a better architecture to get rid of these contributions in lower technology nodes. So basically, this is the question.
Yes. Yes, of course, the best one would be the one that produces less noise, that has better material quality. But that's not always so easy to have the choice. So what usually people do is go for larger area. So you go for a larger area device, because if you go to larger device areas, you have a lower variability of the drain current, or you will have lower noise, and also smaller variance between devices. So go into larger area. So it's very similar to what people do for mismatch. And also interesting is, if you can do that, keep the bandwidth of your circuit as small as possible. Because as we see the case of the PLL, if you reduce the bandwidth of the circuit, you can reduce the noise. So one thing that I can also do is reduce the bandwidth of your circuit, because the variance of the random telegraph noise, and then the current of the current, and then the variance of jitter and so on will decrease as you decrease the time window, or as you decrease the bandwidth of your circuit. I think that's what I can say. A more general comment.
Yeah, looking at the design point of view, as Mr. Shiva asked, I would say that the main thing is that you know what you have in terms of noise, right? You cannot get rid of that. You need to know that it is there, and then you have to improve your design so that the contribution of the noise is smaller, right? I think that's the main thing. Yeah, you cannot get rid of that. It is there. The good thing is that you have. That's the main point, right? And then we come to the next question from Professor Bumpy, which is actually if we can comment on the fat device models using this ring oscillation, and if you have measured the VDD dependence of the three types of jitter in these 5-stage ring oscillators.
Yes, the answer is no. We have not measured it, but we related to experimental results. So that was really only the simulation. The results that I show are only simulation. But if you do the analytical modeling, I did put it here. You can come to an equation that is that the variance on the propagation delay, if normalized to the propagation delay itself, depends on the variance of the drain current over the drain current itself. And here, this is related to the power spectral density of the noise divided by the current square. And if you look at the noise power spectral density divided by the square of the current, you see experimentally that this for the devices increase as you go to lower VDDs. So I would say that it is in line with experimental results. And also there are measurements in the literature that show this, that going to lower operation voltage, to lower VDD, the jitter increase. I cannot remember exactly the reference now, but they are cited, they are commented in our IEEE Access paper. That is this paper there. You can see in this paper there is a detailed discussion on this topic. There is a detailed discussion on this topic. But the main aspect here is really, I say it's not so easy, it's much more, there are much more details than this, but you can imagine if I go to a lower gate voltage, a lower supply voltage, you have the channel formed by smaller number of charge carriers. And then the capture or emission event of a single electrons makes a larger difference. So you can relate it somewhat to have a, let's say, so intuitive view of that to the number fluctuation theory. So it gives some insight, but I know it's not as simple as that, but it helps a lot. I mean, looking in a simple fashion is just what I could say. So the answer is no. We don't have the data for the jitter itself or self, which is related to data in the literature. We would very much like to have data for jitter in ring oscillators and PLLs. We do not have it. We have a lot of data for noise in individual transistors, and there is data in the literature for the jitter on the circuits.
Yeah, the comment from Professor Bumpy. Still going on this model for the noise. Can we trust like the foundry model? Those simulations, those were done with exactly with the foundry model directly, or do we have to some way enhance the model so that we can have a better result?
Yeah, that's a question that, what I can say that it happened many times that people that are interested, that semiconductor companies that are interested in having a better modeling of low frequency noise, they talk to us, and yes, they just say many times people trust so much the models that are implemented, the standard models that you get with your PDK, but it's hard to answer that in a general case. I would say, what I could say that yes, the modeling of low frequency noise, RTN, and the related circuit simulation is still ongoing work, I would say. So it's not yet established. I think
it's not so well established.
It's not so well established.
Okay.
Yes.
Yeah. Thank you. So we'll have another question from Mr. Shiva. So the question was how to choose and use NMOS or PMOS for this design, if it would make it better to use one or the other.
Yeah, it depends on the technology node you are. Many times you see that the PMOS devices are less noisier, but this really depends on the technology. So you need to know the technology. If the PMOS is less noisier than the NMOS, sometimes this happens, but it's not always the case, especially now that we are going to FinFETs, we are going to nanosheets, there's no general rule. I would say for more established nodes, usually people have seen that PMOS devices are a little bit less noisier. But don't take this as a golden rule. You have to look at the noise behavior of the technology you are using.
Yeah, so the best idea is to actually test the device. and check
Yes, yes,
or
and
or
check.
look the model and check to see what you're having, right?
Yes, what you have. Yes, there is no one fit all answer for this. One general answer
Cool.
that will work in any case, in all cases.
So just to show, the other question was related to the mobility, so it's basically the same answer, right? Uh,
Yes, yes, it's a basically the same answer. Yes, but also depends on the trap density. Sometimes you have a lower trap density in the PMOS device. So one is the impact of the trap, and all other is the trap density. That's not necessarily the same in NMOS and PMOS.
Yeah, well, the reason why I asked about the model, the trap model, was that some time ago it was not really included in the foundry models, right? Now we believe that it's still not as good as it should be, but it is included now, right? That's what you mean.
Yes, 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 yes. I would say it's always, in my opinion, it has becoming more relevant, so that it's more usual that's included. But I also would say that is ongoing work, because all what's important, as we see, in my opinion, is you saw there is a lot of variance. So if the foundry provides you only the average, the expected value, well, if you let's look, for instance, a slide with some measurements here. I think we'll be further down here. Yeah, we'll be further down the slide. For instance, in the case of the PLL here, if you are only the average behavior, see here is in log scale. So you have a really large variance. So if you go to smaller area device, of course, if you make your device larger, then it may not be so much an issue. But if you go to small area devices, like we see here, so providing you only the average value may not tell you so much, because let's look here. Let's just assume by I here that the average value is this one. But you may have some device that deviate, the noise behavior deviates by many orders of magnitude. You see, this is 3 orders magnitude above average and 3 orders magnitude below average for a device that is really, it is not really small, let's say so far. It's 300 nanometers wide and 40 nanometers long. And here was much wider one. And even this one that's nanometer size, a micrometer size, you have see a large variance. So I would say sometimes the issue may be not just in the average value, but in the variance itself. So the PDK should allow you also to simulate the circuit not only in the nominal noise conditions, but also, is how it may vary from one device to the other. And I would say this is still ongoing work, in my opinion, what we have seen.
Okay, so well, we don't have additional questions for the audience. But we are very happy with your presentation, with the idea, with the concept, and it's for me as a designer, it's good to hear that we are improving the models and we are getting better results from the foundry as well, right? So it is good that. Would you like to add some final statements for this presentation?
Yeah, just like to thank you very much for the opportunity, and sorry that at the end I got a little faster, because the beginning was slower, so I, I could have been done better, I think.
Oh,
Was able
I
to
think it
explain
was it
better.
was a good pace, and we have indeed a very good discussion, a very good engagement on the presentation. So, well, it is indeed a hot topic, and we have a very very nice presentation. Thank
Yeah.
you very much
And if you
for
have a
for
question, you
for
can send
coming.
me an email. You can send me an email. If
Yeah,
you have a question, you can send me an email.
yeah. So to end, I would like to thank everybody in the audience, and also thank the people that will attend this lecture later, right? Because we have usually a lot of people attending it later. So we have here some thanks from Sergio Bampi, Carolina, from Mr. Shiva, and other people that have not identified directly. And I would like to recommend as well that you take a look at our channel, because we have also other very interesting presentations that you can follow as well. And please look here, we have the email from Professor Gilson, who will be very happy to answer and discuss on this topic even further, right? Thank you very much, Professor. It was a great pleasure to have you here. See you, everybody.
My pleasure, Professor Sandro. Thank you so much. See you. Bye-bye. Was a nice day.
Bye-bye.
Have a nice day. Bye-bye.